Hello, everyone. For this video, we are going to be looking at Chapter 2, The Chemical Context of Life. So basically, this is going to be a summary of biological chemistry and how chemistry um, is used in the biological world. So in this slide here, you'll see this is an image of wood ants, and they are spraying formic acid to deter predators. And so when some sort of predator is trying to eat them or attack them, or if they feel threatened, they will spray this chemical as a form of defense. Um, their most common predator is birds, of course. So this is why they're spraying upwards in this case. So what determines the properties of a compound such as formic acid? Um, First of all, a compound is made of atoms joined by bonds. And here you can see the chemical structure for formic acid. The number of protons that an atom has determines its identity. And then the electrons that are attracted to the nucleus of an atom determines the ability of the atom to bond and how it bonds to other atoms. And it is this formation of a compound and the compound's properties that are determined by this unique bonding pattern that they have to create something unique, such as formic acid. So, our first concept that we're going to go over is that matter consists of chemical elements in pure form and in combinations called compounds. So, organisms are composed of matter. Everything in the physical universe that is living is made of matter. Matter is anything that takes up space and has mass. So if someone ever told you you never mattered, that's not true. Matter is made up of elements. So what is an element? An element is a substance that cannot be broken down to other substances by chemical reactions. It is something that is atomically unique to other things, to other elements. A compound is a substance that's consisting of two or more elements, usually in a fixed ratio. And these compounds can form unique characteristics, which goes back to the theme in biology that um, there are emergent properties that can form when things are bonded together or come together. And these compounds can have characteristics that are different from the elements that it forms. For example, sodium is a metal, it's a soft metal, but it's a metal, which if you try to ingest sodium by itself in a metal form, you would die. It would kill you or be very painful at the least. Chlorine, pure chlorine in nature, uh, is a gas. And you may know of chlorine as mustard gas, which is unfortunately nefarious from the world wars and its use against soldiers and people. But chlorine gas, mustard gas, in its pure form, will kill you. However, but when you combine these two things together, sodium chloride forms, and this is what we commonly call table salt. And we all have and eat too much salt. Um, but it doesn't harm us. It is, we love it. We love the taste. We actually need it. Some organisms need salts to live. So that's an example of something that has an emergent property of a compound. These two different things bonded together will form something new. So there are several elements that do compose the human body and other organisms. About 20 to 25% of the 92 natural elements that are required for life are called the essential elements. Carbon, hydrogen, oxygen, and nitrogen make up the majority of the um, elements that make up a living body, living matter, cells. The remaining 4% is usually calcium, phosphorus, potassium, and sulfur. And then there's another list of elements that are needed, but on very, very small amounts. And so we call these trace elements. They're required by an organism, but only in minute quantities. And so here's a list of the elements in the human body where you can see oxygen, carbon, hydrogen, and nitrogen make up 96% of the elements that make up a biological mass. And then you can see, like, for example, magnesium, 0.1% of biological mass is magnesium, which then makes me question, why are they selling magnesium supplements, like daily magnesium supplements, which honestly is not needed. It's not to say that we don't have or people can't have deficiencies. They do all around the world. There are actually some diseases associated with that, like phosphorus. There's a phosphorus deficiency. There's several different things that can form, but we have to be careful about some of these claims that people may make. So some elements can be toxic to a or organism, depending on the organism. And some organisms have evolved to be able to withstand the toxicity of some elements. And so they have adapted to those toxic environments. And the example I want to give here is how plants have adapted to serpentine. So this is a lily. It's a form of a lily. Um, this lily has evolved to serpentine, which is this greenish rock here. Serpentine is it's a mineral, and so it's serpentine because it's pure form. It looks snake-like. It's a scaly looking. So serpentine is known to be toxic to humans. So, but we would literally have to ingest the serpentine to be to get the toxicity. But plants have evolved to grow in this soil with these minerals and withstand the toxicity. And there are many different examples of species that have um, evolved to withstand toxicity. And later on, we'll learn about uh, bioindicators and species that allow for bioremediation, but we'll get to that later. The second concept we're going to cover here is an element's properties depend on the structure of its atoms. Each element consists of unique atoms. An atom is the smallest unit of matter that still retains the properties of an element. So an atom is the smallest unit of an element. Um, Atoms are composed of subatomic particles, and so these subatomic particles, they can exist on their own, so they don't want to, if you could say that. Um, but on their own, they don't have any specific characteristics. So you have to have a complete atom to have the basic unit of an element, to have the characteristics of that element. So the subatomic particles of an atom are neutrons, protons, and electrons. Neutrons are neutral, they have no electrical charge. Protons are positive, so they have a positive charge. And electrons are negative, they have a negative charge. Neutrons and protons form what we call the atomic nucleus. They form the center of an atom. And it is the neutrons and protons that actually have mass. They have almost identical mass if we tried to measure them on the atomic level. If you had to give them a mass number, which we do, their mass is equal to 1. So one neutron has a mass of 1. One proton has a mass of 1. And these form the nucleus, the center of an atom. Electrons are attracted to the protons of a nucleus. However, they are attracted to it and they form a cloud because they are traveling around the nucleus. And so it forms like a cloud. They actually are traveling in these orbits, but we'll get to that later. That's something you'll cover a lot more if you ever take chemistry. Electrons don't have a mass. Well, they do have a mass, but we don't count it. Their mass is so small, we ignore it when we're trying to do the calculations. So here is some diagrams of an atom. These are two different ways of doing the diagram of an atom. A here is a what we call a cloud-based model, where it's showing you the electrons as a cloud. I don't really like this model. It's not the traditional model, but it's more accurate. But the one that I do like is where the nucleus is here in the center, and you have the electrons shown as a circle. They're actually visibly shown in this model, which I like. When you're trying to learn about atoms and trying to learn about the number of electrons that they have, I like this version better. So here is an overview of an atom. If you don't know, you should learn this diagram. You should learn the parts of the atom. You should know what the nucleus is, that protons are positive, neutrons are neutral, and electrons have a negative charge. So let's go over the mass of an atom again. So atoms of different elements have different numbers of subatomic particles. This is what makes them unique. An element's atomic number is the number of protons in its nucleus. So, like carbon has 6 protons, its atomic number is 6. An element's mass number is the sum of its protons plus its neutrons. Carbon has 6 protons and 6 neutrons, so its mass would be 12. The atomic mass, the atom's total mass, is also its mass number because the electrons really don't add anything to the atomic mass. Uh, let me go back here. Okay, so now we are going to talk about isotopes. All atoms of an element have the same number of protons. However, sometimes um, they can get a different number of neutrons. While it doesn't really change that much, they can add 1 or 2 neutrons to an atom and change the mass of the atom. So one thing that will never happen is you can never change the proton number and keep it the same element. So for example, carbon will always have 6 protons. If an atom was to lose a proton or gain a proton, it would no longer be considered a carbon atom. So carbon will always have 6 protons. However, carbon can have 7 or even 8 neutrons, depending on the situation. And so when that happens, when you change the neutron number, you create an isotope. Now, unfortunately, sometimes you can have too many neutrons, and the isotope will become unstable. And so we call that radioactivity. And radioactive isotopes will decay spontaneously because they can't hold on to the weight. And so they will give off particles and energy until they do become stable. So radioactive isotopes exist and they are potentially dangerous to a lot of biological systems. But let's talk about a positive of radioactive isotopes. Radioactive tracers exist. So radioactive isotopes are used as a diagnostic tool in medicine. Radioactive tracers have been created to track atoms through an organism's metabolism. They can also be used through uh, sophisticated imaging instruments. PET scanners, for example, can monitor the growth and metabolism of cancers in a body. So we have created many radioactive tracers. For example, you can go and you may have something going on with your digestive system that have you to eat food that contain radioactive isotopes. There are radioactive strawberries. I know this exists. Um, or imaging, for example, they will give you, you'll have to get an IV where you'll get injected with the tracer, the dye in your blood, and it will travel throughout your body so that the PET scanners and the other imaging equipments that exist can scan your body and can see what's going on, which we know has been very helpful in the fight against cancer. So this is showing you cancerous throat tissue here in the body. Um, the next thing we are going to talk about is radiometric dating. So this is going back to the idea of radioactive isotopes, where a radioactive isotope is considered a parent isotope and it will decay into its daughter isotope. And this happens at a fixed rate, which we know as a half-life. So a half-life is the amount of time it takes for an element to decay. Um, if we're talking about carbon 14, which is the radioactive isotope of carbon, it decays around every 30,000 years. So every 30,000 years, the amount of parent to daughter ratio, um, the parent will be cut in half, the amount. So it will decay in half. So we can use this to measure the amount of isotopes that are in a sample for, and we can then date it. So in radiometric dating, scientists measure the ratio of different isotopes and calculate how many half-lives have passed since a fossil or rock was formed. So this is how we know how old things are. If we're talking about anything fossil or uh, anthropological, um, how do we know how old things are? Well, we can get estimates. We can get pretty accurate estimates based on the half-life of the isotopes in the sample. Half-lives can vary from seconds or days or even to billions of years. If we're talking about uranium, which has the largest half-life, it's measured in the billions of years. So that's how we know how old the planet is, because we can look at the half-lives, the ratio between the parent and the daughter. And so here's a diagram that's showing you what happens after each half-life. So if we're starting with 100% of the parent at time zero, after one half-life, it will decrease to around 50%. And so each time a half-life passes, the amount of parent remaining is also cutting half. And so it's being converted to the daughter um, isotope. Switching gears just a little. So we're going to talk about energy levels of electrons. So what is energy? Energy is the capacity to cause change. And so there are different forms of energy. One of those is potential energy. It's the energy that matter possesses because of its location or structure. Its structure. That's important when we're talking about biological molecules. But to easily understand potential energy, let's look at it from a location standpoint. A rock sitting on the ground doesn't really have as much potential energy. It will stay there. But if you put a rock on top of a mountain, or if you put a rock on the top of a hill, it will now have a lot more potential energy because it has the potential to roll and move down the hill or mountain. Same thing if you're on a bicycle. If you're on flat ground and you're on a bicycle, you don't really have as much potential energy. But if you're at the top of a hill, you now have a lot of potential energy. So much potential energy that you don't even have to put that much work into going down the hill. And so matter has a tendency to move towards the lowest possible state of potential energy. And this goes back to the laws of energy, laws of conservation of energy and mass. Um, the universe has a natural um, propensity to move towards chaos. The world, nature, and matter wants to move towards chaos because it wants to move towards a state of the lowest possible potential energy. And so this is true for electrons as well. So electrons are found in different electron shells. Shells are like different levels around an atom nucleus. And so electrons can be found in these different shells. And the behavior of an atom and its ability to interact with other atoms and bond is based on this chemical behavior, this behavior of the electrons and its potential energy. So the periodic table here is showing you how the electrons are around the nucleus of each atom. So for example, in hydrogen, hydrogen only has one electron, which will surround the first shell of the electron. Helium has two electrons, and it will fill that first shell. But once we get to lithium, you now have two shells that are formed around the nucleus. Okay, and it will fill up until it gets to 8. Um, from the second shell on, 8 is the magic number for filling these electron shells. And so you can see as we keep going through the periodic table, as we go up in mass number, in proton number, and the electron number will also increase until we get to argon. So this is only the first 2 rows of a periodic table, but there are 7 rows total. And as we keep going down the periodic table, these atoms are just going to get larger and larger and have more shells of electrons that surround them. Now, the outermost shell of an electron, an outermost shell that contains electrons, are called the valence shell, and those are called the valence electrons. These are the most important electrons that are in an atom. It is the outermost shell, the outermost ring around an atom, that will determine the behavior of that atom. And so, depending on the number of electrons, can really shape the way that atoms interact with each other. If the valence shell is full, if we go back to like neon, argon, and helium here, the outer shells are full. If the outer shell is full, we call them the noble gases because they're fine. They're happy being all by themselves. They don't want to interact with anything else. So they are completely fine. And so they are the noble gases, the ones with full valence shells are chemically and they're completely on their own. And that will conclude our first video on chapter 2. In the next video, we're going to go over chemical bonds.